Hello, I'm going to talk to you about the second section of chapter 12. We've done rotational kinetic energy, and now we are going to look at torque. Okay, this is our second week. Okay, so torque, even if it's something that you're not formally familiar with, you know it just by experience. And I usually talk about when my kids were little, unless they were going into a store or something like that, and they wanted to open the door. Um, for us normally now, right? If this is a door you're going to push open, you know to push near the edge of the door. But when you're little, you don't know that, so they would start pushing here, and then they'd push in the middle and push more toward the outside. And so they developed this experience with torque, and actually understood intuitively how it works. After a while of just having trying to open doors. Among other experiences. So we could apply the same force at two locations, right? One close to the hinge, and it's going to be very heavy or hard to open the door, right? We could apply that same force, and the door would swing open, more easily. So what would basically this kind of helps us develop our definition of torque, and a torque is a force that is applied and that produces a rotation. Okay. So there's important pieces that we're building up here, right? One is that we just talked about is where we're going to apply the force relative to where the object is pivoting. So our object is the door, it's pivoting on the hinge. Where we apply the force relative to that pivot point is important. You could also think about applying force this way, right, along the door. And you guys know as well that this is not going to make the door rotate, okay? So that's two pieces of information then, how far the force is placed from the point of rotation, and then also the orientation of the force relative to the orientation of the object that you're trying to rotate. Okay, so those are the two pieces, right? So point distance from the point of rotation and the angle of the force relative to the door. Okay, so again, we can look at this example now with a wrench trying to either loosen or tighten the nut here, right? So there's different showing different ways that a force can be applied here. So we looked at these already, but if I push straight along the wrench or pull back on the wrench, well, pulling back would detach it, but neither of these forces is going to produce a rotation. Okay, and then I can apply forces at other angles, right? This way or this way. It's going to try and rotate it counterclockwise, and if I apply this force or this force, it will go clockwise. If I want to get the maximum rotation for the amount of force that I apply, then I want these perpendicular forces. Okay, that's going to give us our maximum torque. So one thing that we need to keep track of as well is whether a force is trying to produce a clockwise rotation or counterclockwise. Okay, we'll look at that in a second. Okay, so this just kind of reinforces what we talked about in the last slide. So the effectiveness of the force depends on the angle relative to the wrench handle, the effect of the force to produce a rotation. Okay, and even this force, the part we think about this component of the force. There's a component along the wrench handle and a component perpendicular this way, right? It's perpendicular and along. It's only this perpendicular component that produces the rotation. So this brings us to our first definition of torque. So torque is represented with this character here. It's a Greek letter for T, tau. And it's the distance r from the point of rotation to where the force is applied times the perpendicular component of the force. And this equation gives us the magnitude. Okay, so again, here's our wrench example. R is the distance from the pivot point to where the force is applied, and then there's our force. Okay, and the direction of the force or the torque can be counterclockwise, which we will use our convention to say that that is positive, and then clockwise is negative. That's the same sense that we've had for our angles all along, right? Where if we start at the x-axis and go counterclockwise, that's a positive theta, for example. Okay, so in the figure below, right, this force is trying to rotate it counterclockwise, so that would get a positive torque. Okay, now if we have a force applied at an angle, right, we said our definition says that we just want the perpendicular component of that force. So we can think about breaking this force into components, right? That's parallel to the wrench arm and perpendicular to it. And so it's just this component of the force that is going to create the torque. Okay, so we'd have to find out where that component is using our I guess our trig, right, would get us that answer. And again, so this guy, this force is going to try and rotate the wrench clockwise. So that would be in the opposite, the torque of opposite sign than the blue force. And again, we can use this angle between the radius arm and where the force is applied, right? If we imagine sliding that force down here, this angle is the same as, well, the sine of this angle would give us the perpendicular component of the force. Okay. So again, this is just what we said before. So you can think of, F sine phi as the perpendicular component of the force relative to the radius vector. So r, again, is the distance from the pivot point to where the force is applied, and phi is the angle between r and F. And then again, so if we wanted to calculate the magnitude and direction, right, this gives us the magnitude, and then direction, we either say positive for counterclockwise or negative for clockwise. And then torque can also be expressed. So torque is a vector, right? It's got a magnitude and a direction. It can also be expressed in terms of a cross product. So this is a vector multiplication that we haven't seen before. So again, we're taking the vector r, we're using the cross product to multiply with the vector f. Okay, so the magnitude is still the same. It is still rf sine theta, or sine phi, sorry. And then the direction, so we've talked about using either clockwise or counterclockwise. We can also think of the torque having a direction in the third dimension. So if our radius vector was in this direction where, let's say, A is pointing, and then our force is in the direction of B, our torque would actually be in the direction of your thumb. Okay, so you can do some practice with this, right? So you want to have, oops, sorry about that. So you would, have your pointer finger in the direction of R, your middle finger in the direction of B, and then your thumb shows you the direction of the resulting torque. And then if we need to represent the third dimension on our two-dimensional page, we can use, this is basically like an arrow head. So you're thinking of like the point of the arrow coming toward you, that would be out of the page, and then the tail fins of the arrow going away from you for something that was moving into the page. Okay, and the cross product does apply to any two vectors, right? So when you get to Calc 3, you will learn about this as just a way of combining vectors. We have seen the dot product, so that's a way of combining vectors where we get a scalar at the end. The cross product is a multiplication of vectors that produces a vector at the end. Okay, so it depends on the magnitude of A, it depends on the magnitude of B, and then the angle between them, right? The sine of the angle between them. So in this case, A and B are in the same direction. The angle between them is 0. Sine of 0 is 0, so the cross product is 0 in that case. Here we do A and B where they have an angle between them, let's say, of 30 degrees. And then we take the magnitude of A, the magnitude of B, the sine of the angle between them, which is 30. Right? So we'd get 1/2 A times B. And then we can get the maximum cross product when the two vectors are perpendicular to each other. So again, we take the magnitude of A, the magnitude of B times the sine of the angle between them, which for 90 degrees would be 1. And so the cross product in that case is equal to AB. Okay, again, remembering if you want to do it by hand, your pointer finger is in the direction of the first vector A, let's say, then your middle finger, I can't personally separate my middle finger from these two, so I do the rest of my fingers in that direction of B. And then torque is in the direction of your thumb. And we'll do, this is much easier to practice in class than over a video, so we'll do some more of that in class. And that's something we'll talk about in class. Okay, so if you have an extended object, and in this part of the course we are dealing with extended objects, we're not thinking about things just as point sources anymore, right? So we talked about the center of mass, and let's say you had this oddly shaped thing, and it's pivoting about this axle R, okay? So the center of mass is shown here, right? So this is where if we wanted to represent the object just as a point, that's where we would put it. And you can see that the center of mass in this case is offset from the point where it's pivoting on this axle. And so if you held something like this, you'd expect it to rotate actually. And so that rotation is actually arises from the torque due to the center of mass weight. So, okay, so we can find the gravitational torque, right? So we would want to think about the force of gravity being applied to the center of mass. So there's a force right here. And then there's some distance from the pivot point to where the center of mass is. That's our vector r. And then this shows us the angle between them, right? So we can use this expression that the magnitude of the torque is Rf times the sine of the angle between them. Here I'm just going to swap F with mg, and R with, is just moving over to the side. Okay, and then just to show you where we get to here, right? So this, if we look now at R sine phi, it's actually this distance. It's just kind of another way of looking at the torque. And that, in this diagram, is just how far in the x-coordinate is the center of mass from the point of rotation. Okay, so our direction would be clockwise, right? So this, we expect this to fall downward, to rotate downward. And so that would, get a negative direction for torque. And then this just kind of puts it together now with the sign, right? So the torque due to gravity is negative mg times the x horizontal distance from the pivot point to where the force is applied. Okay, and if this center of mass is not supported, right? So if this was resting on some kind of surface, it would stay where it is. But if it's not supported, then we're going to get a rotation. Okay, and if we wanted to calculate some quantitatively what that rotation would be, we use actually the analog of Newton's second law that we've seen so far, right? F equals ma, but now we have one that is for rotation. So this is saying our angular acceleration alpha is the net torque on an object divided by its moment of inertia. Okay, so in linear terms, we would have had acceleration is the net force divided by mass. So remember we said moment of inertia is our rotational analog of mass, and then torque are the forces that are going to cause rotation, and then this is our rotational acceleration. Okay, so if you have a non-zero torque, you're going to get an angular acceleration. There are some examples that are done in that Dr. McColgan has done as videos to where we have acceleration. We'll do some of those in class. And then the rest of this video is going to focus on what happens if you have the net torque of 0, right? So we don't have, and in particular, we're going to look at the case where there's no rotation at all, right? Just like with forces, if we had a net force of 0, we could move with a constant velocity. And then also, or we could have a velocity of 0. Okay, and again, just to highlight the analogous quantities, right? For rotational dynamics, we have torque. These are forces that produce rotation. In linear, they're just forces. Moment of inertia is an object's resistance to rotation. Mass is an object's resistance to acceleration. If we have unbalanced torque, we get an angular acceleration. If we have unbalanced force, we get linear acceleration. And then again, alpha is the net torque divided by moment of inertia. Linear acceleration is the net force divided by mass. Okay, so there is a big field of engineering that's based on static equilibrium, right? So, and this is a special case of equilibrium. Static means that it's not moving. So there's no net force, there's no net torque, and there's no motion, right? So we're not talking about constant angular motion or constant velocity, linear velocity. It's all staying still, right? So this is the kind of situation you'd want if you have a bridge or you're designing a building or some architectural arch as well. So it is the foundations for fields, a lot of big components of civil engineering, structural engineering, architecture. Okay, so if we want to solve problems that are in this particular scenario, right, where we don't have linear motion and we don't have any angular motion, right? So static equilibrium. So there are criteria for this, which is that the net force has to be 0 and the net torque has to be 0, right? So this is a new piece that we haven't had before. So what we're going to do, instead of writing just a free body diagram, we're going to draw extended free body diagram. So we're actually drawing the whole physical length of the objects that we're analyzing. We can pick any point as we want as the pivot point, and the net torque, and this is because net torque about any point has to be 0, right? So we can pick a pivot point that's convenient for us. We can calculate the torque about from all the forces that are applied to the object, and then we start applying this. So we'd have, from the force equation, we actually have our two equations, right? Some of the forces in the x has to be 0, some of the forces in the y has to be 0, and from the torque equation, we know that the sum of the torques has to be 0. And so we'll be able to use those 3 equations to solve for any unknowns. Okay, so here's our first example. So we have 2 objects that are suspended from a rod. Okay, and we don't actually know what the values are. We know M1 and M2, and we know M1 looks bigger than M2, right? And so the question is where, if we assume that the rod is massless in our first example, where would we have to support this, right? So imagine this is like some kind of mobile or something. Where would you have to support it so that it is balanced? Just draw it here, my picture, and we have, so it's showing that the origin is going to be, we're just going to set up our problem so that the origin of our torque equation is where we want the rope to be. Okay, so we expect everything to be balanced relative to that. Okay. Okay, so also in the picture, right, it showed this as R1 and it showed this as R2. And it asked for just to an expression for the ratio of R1 and R2 compared to the ratio of the masses. Okay, so our extended free body diagram. So this is what we're going to draw out here, right? So this is my picture. Now I'm going to do my extended free body diagram. Okay, and I'm just going to show where the forces are actually applied along the length, right? So this is, let's say, force of gravity 2. This is going to make it a little bit longer. This would be the force of gravity 1. And then here's my origin. So there's going to be some kind of tension, right? If it's hanging by a string, that should be pretty long, actually. It should balance out those other two forces. So I'll just call that tension. Okay, and then this is my origin. And of course, with you want to set our directions, right? So for counterclockwise, we're going to say it's positive. Clockwise is negative. And then we should also have our X and Y coordinate axes, even though we don't really need it in this case. Okay, so these are all parts of setting up the problem. Okay, so now we can apply our torque equation. So for this two hanging masses to not be flipping around and rotating, the sum of the torques has to be 0. And so we're going to use, again, this point where the string is attached as the origin. And so if we think about that, so the way you want to think about it, right, is like holding, let's say my pen is the rod, right? So I want to hold it fixed at wherever my origin is and then see which way the rod's going to rotate due to the different applied forces. So if I push down the way 1 is, I get a counterclockwise rotation. Okay. And if I push down the way where 2 is on this end, I'm going to get a clockwise rotation. So 2 is clockwise, it's a negative torque, right? And 1 is counterclockwise, so it's positive. So I get the torque from 1 minus the torque from 2 has to be 0. Okay, and then that torque is R1, F1, sine of the angle between them, minus R2, F2, sine of the angle between them. And that's going to be 0. And in both cases, R and F are actually perpendicular. Okay, so sine of 90 degrees equals 1. So both of these just go to 1. Okay, and then I have R1, F1 minus R2, F2 equals 0. And now for the forces, I can put in mg, right? So R1, force 1 is m1g, and that's on the other side. I bring this over to the other side, add it to both sides, and I get R2, m2g. Okay, so I have a g on each side. I'm going to cancel that out, and I'm going to divide through by R2. So I get R1 over R2 times M1 over here equals M2, and then we divide by M1. So we get R1 over R2 equals M2 over M1. Okay, so that's our first example. Okay, so let's do another problem. So now we have a seesaw. 3 children are trying to balance on a seesaw. So we have a fulcrum and a rock. All right, so we're just going to draw kind of a long board, and we have a fulcrum in the middle. Right, that's how seesaw works. It's just like a little pivot point in the middle. And then, so we know that the length of the board is 3.2 meters. Okay, so 2 boys are already on either end. Boy A has a mass 45. kilograms, okay. And B has a mass of 35. Okay, and then we're going to add a third child, a girl, who has a mass of 25 kilograms. And the question is, where should the girl sit to keep the seesaw balanced? Okay, so here's my seesaw. And this is what I'm given over here. Right, and we have to find, let's say, RC, right, where the third child should sit. Okay, so I'm just going to put child A over here, let's say. And we'll put B over here. Okay. And so if A is heavier, right, this side is going to come down. It's just like a little balance. So we know somewhere that the third child's going to have to sit somewhere on this side. A little smaller, and that would be C. Okay, and then this is the distance. I'm going to say that this pivot point is my origin. Okay, so that's my distance to for child A, right? And then we'd have a distance to child B from the point of rotation to where the force is applied, and same thing for C. Okay, so that's just kind of our picture. Now we want to draw our extended free body diagram. So we're just going to draw this as flat. Okay, and then, all right, so we have a force applied at one end, right? So this is our, draw it like that, and we'll just call it the weight of A. And then we have another force applied here, and the weight of B. Okay, and then this is my origin. I'm going to put right in the middle of the board. So there is actually a weight of the board too. Okay, and then somewhere, we don't know where, we're going to put the weight of child C. And then right at the pivot point, right, the fulcrum is going to produce a normal force that's going to balance all of these. So it's actually going to be super huge the way I've drawn all this. The normal would be way up like that. 1, 2, 3, 4, 5, 6, 7, 2, 4, 5. Yeah, about that. Okay. Didn't plan that out very well, but that's kind of how long the normal would be. Okay, and then I am going to, I don't know the weight of the board, and I could figure out the normal force if we wanted to, but I'm just going to put the origin there. And so as you're setting these up, you can think about putting the origin at a place where you don't know one of the forces, because when we do our distance from the origin times the force, that distance is always going to be 0, right? For any force that's at the origin. So that will go out of the torque equation. Okay, so we're again going to set up our coordinate axes, right? So we have X here and Y here. And then for our torque direction, right, we're saying counterclockwise is positive and clockwise is negative. Okay, so we know already that the board and the normal torque are going to go to 0. So then we can sum up the rest of the torque. So sum of the torques equals 0. Okay, and then so again we think about fixing the board in the middle, right? And then we push down where A would, on the side that A would push down. We get a counterclockwise rotation. So A is going to have a positive torque. B is going to sit down here, right? And it's going to, oh, I'm blocking myself. B is going to rotate it clockwise. And then if I go back and say C as well is going to rotate it clockwise. So B and C are getting negative torques. So I add the torque of A, I subtract the torque of B and the torque of C. Okay. And then so we have, for each of the torques now, we have R times the force, right, is going to be the force of gravity. So MAG times the sine of the angle between them. And then RB, the force B, which is MBG times the sine of the angle between them. And then we get the distance to C times the force exerted by C is MC times the acceleration of gravity times the sine of the angle between them. And those have to equal 0. I kind of ran out of room on that side. Okay, so for all these cases, right, if I look at the radius vector and the force, they're always perpendicular. So all of these, like we just did, all of those signs go to 1. Okay. All right, and then remember, this is what we're trying to solve for, RC. So let's move that onto the other side. So we have RA, and we cancel out the G's, okay, MAG minus RB, and BG is going to be equal to RC and CG. Okay, and then we do have acceleration of gravity, right? So we can divide that everything through. I have 1 in each term up in the top, so that goes away. So I get RA MA minus RB MB equals RC MC. So I can now just divide by the mass of child C. And we're getting really close here now. So RC equals RA MA RB MB. Okay, and what are RA and RB? They're actually the same, right? They are the length of the board divided by 2. Maybe that is our whole length. Okay. So I can, so I get, let's say, L over 2 MA minus L over 2 MB divided by MC. So I can actually factor out now that L over 2, and I get MA minus MB divided by MC. So if we plug in now, we have 3.2 meters for L divided by 2, and then we have the mass of A is 45 kilograms, child B is 35 kilograms, and child C is 25 kilograms. And if we plug that in, I think we get like 0.6 something. I did this already, so just to save us some time. 0.64. Okay, so that is the position from the pivot point, right? We're going to go 0.64 meters, and that's where the third child should sit. Okay, got one more example. You guys are still hanging in there. Okay, that's kind of solved there for you. Okay, so the last example is a weighted hand. This is kind of interesting. It really surprised me when we first did this problem. Okay, so we have a question. So basically you're holding a bowling ball in the hand, right? And this is actually the details of how the bones and muscles are attached. So your bicep is attached a certain distance. We're going to estimate it to be like 3 centimeters from your elbow. And then you have the length of the forearm, we're saying is 35 centimeters, and a ball that weighs 50 newtons is you're supporting. So the question is, what force does the bicep exert to hold this up? And then there's actually a reactive force from the upper bone as well. And we want to find out what both of those are. So we're going to model the forearm just as a rigid bar, right? And the upper arm as well, right? So we have these 2 bars, but we only really care about the bottom one. This is what we're doing the analysis for. Okay, so we have the force of gravity down at the end. Sorry, that thing keeps going in there. We have the bicep that's going to pull up, and then we actually get a reactive force from the upper arm that's pushing down. Okay, so let me just sketch that out here, and then we'll go to write down what we're given. So we're given that the mg for the ball is 50 newtons. Given that the distance from the pivot point to where the bicep attaches is 3 centimeters, and the length of the forearm is 35 centimeters. And we'll just redraw. Okay, so we have an upward force from the bicep, we have the weight of the ball going down, and then I'm going to have a reactive force from the upper arm as well. Okay, so let's go to our ladybug camera. Okay, so I just kind of sketched that in quickly, and so we are going to set this as our origin. Okay, so we want to find the force from the bicep and the reactive force of the upper arm. Okay, so again, we're going to say, we can set up if we sum our forces. We're going to set up that that's our x and that's our y direction. And then also we have counterclockwise is positive and clockwise is negative for our torque. Okay, so we have our extended free body diagram, we have our coordinates, we have our given and our find. So let's go. So the first thing we're going to do is I'm going to solve the torque, right? So remember our conditions for static equilibrium. We have the sum of the forces is 0, right? So that means the sum of the forces in the x equals 0, the sum of the forces in the y direction is 0, and then also the sum of the torques has to be 0 for it not to be rotating. I'm going to start with this one because we actually have two unknowns in terms of forces, right? So my torque equation, sum of the torques is 0. And I don't know F and I don't know R, so I'm going to put my origin at first at where R is, and then I know that falls out of my torque equation. Okay, so let's figure out our sign. So if we look at the mg, so I'm going to hold it fixed where my origin is, and then apply the force in the direction mg would do, so that's a clockwise rotation. So mg gets a negative torque, and then the force from the bicep is up, that's going to go counterclockwise, so that's positive. So I get the torque from the bicep is positive and minus the torque from, let's say the ball, whatever, and that has to equal 0. And I know the force from R is just going to be 0 because there is no lever arm there, right? It's at the origin. Okay, so then I do RF times the magnitude of F times the sine of the angle between them minus the radial distance to where the ball sits times mg of the ball, right? That's its force times the sine of the angle between them equals 0. And again, we're in a situation where our radius vectors and the forces are perpendicular. So our signs are all going to go to 1. Okay. And this is our unknown. We actually know what R is, so let's get this by itself. So we have RF times F, and we're going to bring these over to the other side, equals RB times mg. Okay, and based on my diagram here, right, this actually was given as D, and then this was given as little l, so we should put that in there. So this is actually D, and this is little l. So D times F equals L times mg. So now we can solve for F. We divide through both sides by D, so I get L over D times the weight of the ball. And so we can plug in. So that is, L is 35 centimeters. And since I'm just doing a ratio, I don't need to change the units. They're going to cancel out. 35 centimeters divided by 3 centimeters times the weight of the ball. 50 newtons equals F. Okay, and let's bring up our window. Yeah, I did that already. Okay, 50 times 35 divided by 3, so we get 583. So this really surprised me. I don't know about you guys, but to think that you are exerting 10 times the force to pick up a ball, but that your bicep muscle is exerting 10 times the force, that's kind of crazy. Okay, so now we still want to find R, and so now we can go to R. There are no forces in the x direction, so this equation doesn't really help us, but we can use this now to sum the forces in the R direction and find out what R is. So if we do the sum of the forces in the y direction equals 0, then we have the force exerted by the bicep minus the reactive force minus the weight of the ball equals 0. Again, we want this by itself. So I'm going to add that, bring that over to this side. It equals the force minus mg. Okay, and then I'll just swap sides because I like my thing I'm solving for on the left. So we have 583 newtons minus the weight of the ball, 50 newtons. And so we get the reactive force is 533 newtons. Okay, and there we go. So your arm's working pretty hard, right? The upper arm is pushing down at 533. The bicep muscle is pulling up at 583 just to lift that ball. And I think that's enough. So be sure to check out the other worked examples that Dr. McColgan has already posted videos of.